Okay, my dear students, Assalamu alaikum. Let's move on to the next lecture on complex variables, which are very useful in solving integrals. And you know that if you learn how to solve an integral, it means you are able to solve a differential equation. So that is our main target. Okay, now today's lecture is from chapter number 6, and it is page 365 from the third edition of the book by Arfkan. You can also consult my notes, which I have already sent on this chapter, and you can see the picture of these notes. Now this is in fact page which I will take up today. In the previous lecture, whatever we have introduced for this chapter, you can also find that detail from my notes. Okay, now this is today's topic, the Cauchy integral theorem. You can go through from the book as well, Cauchy integral theorem. But let me explain from my notes. The Cauchy integral theorem. First of all, let us define what is a contour integral. So, a contour integral of a complex function over a contour in the complex plane. Now this is the contour, this line, a journal line, on which we want to integrate a certain function from the point z0 to the point z0 dash equal to zn. So we have divided the contour z0, z0 dash into n intervals. So we have n small intervals by picking n minus 1 intermediate points z1, z2, z3 up to zn. And let us consider this sum. What is this sum? We have taken the value of the function at the midpoint of any interval. Here it is the jth interval, and we have multiplied this with the length of the interval, which comes out to be zj minus 1, and then we have taken this product over a certain sum from j is equal to 1 to n. That is, we are summing up this product over the entire contour over here. So here eta j is a point on the curve between zj and zj minus 1. Now let us take n going to infinity, that is, the intervals are very small, such that zj minus 1 absolute, which is the length of the interval, tends to 0 for all j. Now under this condition, if this sum Sn exists, now listen carefully. So if the sum Sn exists, it means that, and is independent of the details of choosing the points zj and eta j, then the limit of this sum n tending to infinity is called the integral, the definite contour integral of the function f of z dz from the point z0 to z0 dash. Okay, so that was the definition of the integral, contour integral. Now let's come to the Cauchy integral theorem. Now this is the statement of the theorem. If a function f of z is analytic, which means it is single valued as well, and its partial derivatives are continuous throughout some simply connected region R. So we have a simply connected region R, which you can see from the book as well. So there is a region R Let me show it from the book. Okay, so this is the region R over which the function is analytic. So that is the requirement of this theorem, that if the function should be analytic on at every point on the boundary and also at every point within this region R. Okay, so if the function is analytic, then for any contour taken within this region, as is the contour C over here, it is a circular contour, then the statement of the theorem completes by saying that now this region is called the simply connected region R. Then for every closed path C in R, the line integral of f of z around C is always 0. So that is the statement of the Cauchy integral theorem. So the integration goes to 0 for every closed path C, not necessarily a circle. It can be any closed path within the region R over which the function is analytic. Then this integral is always 0. So the proof, there are two proofs. One uses the Stokes' theorem. So in this form, Cauchy integral theorem may be proved by direct application of Stokes' theorem. We know that f of z has the real part u and the imaginary part v, and dz is equal to dx plus itv. So if we substitute these values for f of z and dz here and multiply and simplify and separate the real part, this is the real part and this is the imaginary part, then we also use the Stokes' theorem. This is the use of the Stokes, this is the statement of the Stokes' theorem. So if we take Vx is equal to u and we take V is equal to minus Vy and apply this over here, then the real part of this integral is equal to this, and then by CR condition, this term is equal to this term. That is the CR condition, because the function is analytic in the region, so the CR conditions must be satisfied. So this is the first CR condition, and it makes this equal to 0. So it means the real part of the integral is 0. Similarly, using the second CR condition for the imaginary part, we see that this is also equal to 0, as is explained over here. So when the real part is 0 and the imaginary part is 0, it means the function, the integral of the function over the closed contour is equal to 0. So that completes the proof. So the statement of the proof. There is another proof over here, Cauchy-Gorset proof, which you can go through yourself, but the result is the same. So we have given the statement as well as the proof of the Cauchy integral theorem. Now this statement was with reference to the simply connected region. Now mind you, if we do not have a simply connected region, which is like this, so in this region R, the function contains, the region R contains a problem region R dash. Inside R we have a region R dash for which the function is not analytic. Okay, if we have a situation like this, that the region contains a problem region, and of course if we take a contour C, now we cannot use Cauchy integral theorem, because the first requirement that the function must be analytic at each point within R, and this contains the region in which the function is not continuous. So we cannot apply Cauchy's integral theorem for this contour, and this region is known as the multiply connected region. That is a region containing a problem region. So what should we do for this? So what we will do here is that we will somehow exclude the region R dash from our contour. So if we can do that, this closed contour is modified in such a way that the problem region is excluded, and this has been done here. Okay, so this is the same contour. We have started from a point A of this contour. Now what we have done here, we have drawn a line from the interior region to the outer problem region, and we call it the cut line. It is not clear in this diagram, but you can imagine that there is a line crossing R dash through up to the, and we start our contour now from a point immediate above this line. Okay, so this is the point A, starting point. We go around this region, this contour, and we come back to the point D through the point B, and this point D is just below the cut line or the other side of the cut line, and then we take a horizontal tour along this cut line inwards, and we do not cross the region R. We end up with a point E over here. As you can see, you can get this picture clear from the book. Let me show you this picture from the book. Okay, here is the picture. So and then we have, now we travel from the point E to through the point F to the point G, just on the opposite side of this cut line, and then we travel back to the point A. So we have modified our contour, consisting a larger circular path, and then two horizontal paths, and then a path around another closed path around the problem region. And so it means if we go as, say, A, B, D, E, F, G, H. So this modified path does not contain the problem region. We have excluded the problem region, and therefore we can apply Cauchy integral theorem for this entire path. And now you must also note that the travel from the point D to E and the travel from the point G to A are opposite, and the integration over these two paths cancels out. So we are left with two circular paths, the C1 dash and the C2 dash. Now mind you that C2 dash is being traveled clockwise, and you know the integral for this will be negative, and the C1 dash integral will be positive. So we will have the integral over C1 dash minus the integral over C2 dash. If we take it negative, it means now C2 dash has also been is also being taken along the anti-clockwise direction. So we end up with this equation 6.42. So these two integrals are then equal, and this is the application. This is the Cauchy integral theorem as applied to the multiply connected region. Okay, so this is also equation 6.42 is also a very interesting result, because the first term, the first integral over C1 dash, which is on a larger closed path, is equal to the integral of the function over the smaller closed path. So whatever path we take, if it is closed, then this will be equal to 0. Okay, they will be equal. So after that, I would suggest that you solve the exercises 6.3.1, 6.3.2, mark these exercises, 6.3.3, 6.3.4, 6.3.5, and so on. So I will come back to the solution of these problems, but you must keep on trying as a group or individually. You can also consult other books on complex variables to solve these integrals. So let me end here as the first part of today's lecture. I will present another part in the next video. Okay, thank you very much.